Let's take a few minutes to talk about using reversible and irreversible arrows in our mechanistic steps. So let's look at each of the four patterns in turn. So here's nucleophilic attack. If we have this cation and water, and we are expecting a nucleophilic attack pattern, of course, that's going to look like this. And I've already drawn the product for you. And it's important to recognize that we have a good leaving group attached to our molecule now. If I drew that arrow, and I'm going to erase it in a second, but if you can envision me drawing that arrow, that's just going to go backwards to our starting material, cation and water. And so that tells me that this reaction is probably reversible. The leaving group can leave. It's a good leaving group. I'm sorry, this is the nucleophile here, and here it's acting as a leaving group. And so generally, nucleophilic attack reactions will be reversible when we have a good leaving group in the product. Here's another example where we have a nucleophile. The CH3- is our nucleophile. It's going to attack the partially positive carbon on the carbonyl. That's going to get us to this structure. And now we're going to ask ourselves, is that methyl group that we added a good leaving group? Could this reaction go backwards to the left to reform the carbonyl and the methyl anion? And hopefully you recognize this as a very strong base. If you look up the pKa of methane, the conjugate acid of CH3-, you'll find that it's somewhere around 50, so it's not a very good acid at all. It's very stable. So a carbon anion is often going to be very reactive and a very strong base, and in this case, a very poor leaving group. So we're not going to use reversible arrows here because this reaction is not going backwards. We are not going to see the O- suddenly drop down to form a carbonyl and kick off the methyl anion because that methyl anion is such a poor base. So we're not going, I'm sorry, it's a really good base. It's a very poor leaving group because it's so unstable. It's such a reactive base. So nucleophilic attack, we can use either of them. It really depends on how the product looks. In this case, it looks like it has a good leaving group attached. In this case, we can't even tell which of those methyls was the one that was added. They're all the same. And the methyl anion is not going to be lost. So if we look at loss of leaving group, of course the arrow push for that is a simple arrow like that. We lose chloride, we end up with this tertiary cation here. The question we ask ourselves here is, can the chloride be a good nucleophile? Is the chloride a good nucleophile? And I hope you answer that it is, yes, indeed a good nucleophile, and therefore loss of leaving group can just as easily be nucleophilic attack if I use that arrow and we envision the reaction proceeding to the left. So I'm going to erase that arrow. We don't normally include that, but you could see here that the chlorine could potentially act as a nucleophile. So often, most of the time with loss of leaving group, we use reversible arrows. Here's a couple of proton transfer reactions. So this anion is grabbing the hydrogen, and we're producing butane and OH-. In this case, the pKa's of the acid are useful to deciding whether or not this is reversible. So I have 15.7 for water and 50 for butane. So the difference is approximately 10 to the 35 order, 10 to the 35th, which is 35 orders of magnitude. So a significant difference here. Let's compare that with the other proton transfer I've prepared to look at. So here, 15.7 and 18, the difference here is 10 to the 2.3. So a much closer difference in acidity, a much closer acidity levels. Typically, if the pKa difference is 10 or more, so like here, the pKa difference is 35. It is irreversible. So here, we could use reversible arrows, and I would say that most of the time when we're trading hydrogens between oxygen atoms, which is a very common occurrence in a lot of our mechanisms, we'd use these reversible arrows. When we start with a C minus and then we create an O minus, that's when it's time to be irreversible. So a lot of times in our class, proton transfers will be reversible. And lastly, rearrangements. Of course, that's when the hydride shift happens, and that takes the electrons from the CH bond and plops them into the empty cation, and that creates a tertiary cation from a secondary cation in this case. And so we know that the tertiary cation is much lower in energy. And so generally these are going to be irreversible. We don't really see any cation rearrangements that are reversible, because we know that a tertiary cation does not rearrange into a secondary, and that's what would happen if I were to indicate that this is reversible. So I'm going to erase that second arrow. It is not reversible. Just about all carbocation rearrangements are going to be irreversible, requiring just one arrow pointing towards the products.